So it's a real pleasure to be able to come here and speak to you all about some of my work. So I'm a PhD student in the Department of Statistics here at CMU, where I'm advised by Aditya Ramdas, who is also a co-author on this work. And that work is entitled Estimating Means of Bounded Random Variables by Betting. So consider the following problem. Given bounded random variables x1 through xn with some common mean mu, the goal, broadly defined, might be to produce a set Cn, which is a random set. It's a function of x1 through xn, such that the probability that this value mu is not in Cn is at most alpha. Think about alpha as something small like 5%. Or equivalently, you could say that this probability, that this statement is saying that the probability that mu is inside this set Cn is at least 1 minus alpha. So if alpha is 5%, then this is saying that this is captured with 95% probability, or at least 95% probability. So this is nothing more than a confidence set or a confidence interval, as you might be familiar with them. Although this is a little bit different than what's typically taught in, say, like Stat 101, because there we'll typically use some sort of asymptotic normality arguments using the central limit theorem. But here, this is an exact finite sample confidence interval or confidence set. So Hooftings inequality actually provides one solution to this problem. So this is Hooftings. This is a confidence set that results from Hooftings inequality. This was an inequality developed by Wassily-Hoofting in 1963, which it's a very simple set. It takes the form a sample average plus or minus this margin, which looks like square root log 2 by alpha over 2n. Yeah. Yes. Yeah. Exactly. So I didn't say that here, but I'll make that a bit more formal later. Yeah. Thank you. So this is one solution. So this actually provides a solution to that problem that I said on the previous slide, but the downside here is just that it's not a very sharp solution, especially for random variables with small variance. So we'd hope that if we have random variables that maybe they're bounded, but maybe they have a smaller variance, then maybe we'd be able to get tighter and tighter confidence sets. But in this case, as you can see, if you just look at this expression, there's nothing said here about the true variance or an estimated variance, empirical variance, or anything like that. So this is not able to adapt to those smaller variances. So we might want to restate the previous goal as just given bounded random variables with some mean mu, produce a set with this coverage probability, and make the set as sharp as possible. So this is broadly going to be the overarching goal. No, they're not, but you can think about them as independent for now. But I'll mention what deviations from independence will make. So here's the outline. So basically on the next slide, I'll just give you the punchline and maybe some motivation for why you might want to care about this problem. And then next, I'll talk about betting and confidence sequences, which I will almost certainly be able to get to and finish. And then after that, I'll talk about the fixed time regime, where if you don't care about sequential inference, so section 2 will be more like sequential stuff. Section 3 will talk about fixed time confidence intervals using sequential ideas, even if you didn't care about them. And then I think it's unlikely that I'll get to the last two parts of the talk, but we'll see how it goes. But if people are interested, I definitely have like backup slides and stuff like that. But the main talk will be the first three. So first, I'll just tell you what the bound is. So this is essentially the bound that we'll talk about throughout the talk. It'll take various forms. There'll be slight deviations from this, but this is the moral idea behind it. It's really just the sub-level sets of this product function. So it takes the form of a product, 1 plus this lambda, which we'll design later, xi, the data that we're observing, minus m. And so this m is basically the thing for which this is a function of, and then we're looking at its sub-level sets at level 1 over alpha. So it should not be necessarily obvious as to why this is correct or why it's good or anything like that, but I just wanted to write it down so you see how simple a form it can take. So it might also look a little bit weird because it's like this implicit bound. Right? It's not like closed form or anything. It's just these sub-level sets. But it turns out that the Hoofting bound that I showed you a little bit before takes almost the exact same form. It's often not written in this way, but it does take this form of like the set of all m such that some product function of m is below 1 over alpha, but with some specially chosen lambda, which I won't talk about too much, but this is essentially an instantiation of the Chernoff method and Hoofting's version of it. Okay, so that was the bound itself. Now let me just talk about some of the empirical results. So here, like was said before, if you have bounded random variables on A and B, say, then you can always just shrink that interval and send it to 0, 1. So you can always consider bounded random variables on the unit interval 0, 1 without any loss of generality. And so hi, this, okay. Yeah, okay, great. Thank you. So yeah, that's good. So if you have bounded random variables on 0, 1, then the largest variance it can have is a quarter. And this is achieved by having a Bernoulli 1/2, okay? So in this regime, Hooftings inequality is already rather a tight bound because it is sort of targeting like a worst case variance in some sense. So here are some various confidence intervals. So I'll focus on ours and Hoofting. So I'll actually just zoom in on this. So here, in the case where Hoofting is already quite tight, ours is either matching or just improving on Hoofting at least a little bit. And so the way in which we can improve on Hoofting just a little bit in this regime will be clear later. But the takeaway is that Hoofting is already rather tight in this regime, and so we're basically matching or improving on it. The story changes when we have this really small variance distribution that has like a variance of 0.0046. If we zoom in on this, you see Hoofting doesn't change, right? Because the width of that thing, it doesn't actually change depending on what the true variance is or what the empirical variance is, whereas ours is able to adapt to the variance and greatly outperform Hoofting and also these other bounds that we considered in the literature. Okay, so this is basically the punchline for all these fixed time confidence intervals. So now I just want to go on a quick detour, really short, but on some applications. So unless you live and breathe confidence intervals, p-values, hypothesis tests, and things like that, you might not necessarily know why or care like why confidence intervals for bounded random variables is all that interesting. It turns out a lot of problems, a lot of very practical downstream problems actually have this as part of its like core elements, or it really reduces to this problem of bounded random variables. So I'll give two motivating examples. The first one, this is not my work. This is work by Stephen Bates, Anastasios Angelopoulos, Lihua Lei, Jitendra Malik, and Mike Jordan. I think that's it. Might be missing someone, but they were essentially concerned with this problem of constructing prediction sets for tumors. So they would be given these images of potential tumors, and they would basically be tasked with this image segmentation problem. Tell me where in this image is a tumor, tell me where it's not a tumor. And so they would be able to use any sort of black box machine learning algorithm, and they're operating in this, this world of conformal prediction, where the white regions here, these are the predicted tumors. The black regions are the predicted non-tumor regions. And if you see this sort of, this like little green region around some of these, this is sort of like, this is an uncertainty set or a prediction set. And so what they're doing is they're constructing these prediction sets that are able to control some notion of risk with high probability. And the way they control that risk with high probability is through a confidence interval for means of bounded random variables. And so they actually used many different bounds in the paper, but one they considered was ours, and ours was quite effective for this problem. And in this problem, the tightness of a confidence interval directly leads to sharper prediction sets. So this is why you might not only want to care about this problem of confidence intervals for bounded random variables, but also why you would care about the sharpness of those intervals. So here's another motivation. This one is my work with Philip Stark and Adi Ramdas. So this was a very different application where we were looking at election auditing. So we would have, say, maybe an electronic voting machine would report that maybe Biden beat Trump in some region. And then we would say, okay, maybe the electronic voting machine can't be trusted. Maybe it was tampered with. Maybe there's a software glitch. It like was disconnected from its power supply, something like that. And so we want to do an audit, which is to basically look at a random sample of the ballots and say, is this congruent with what the electronic voting machine had reported? And so it turns out that this problem reduces to constructing a confidence sequence. So I don't expect people to know what that is. I'll definitely go into that, but think of a confidence sequence as a sequence of uniformly valid confidence intervals. And so it reduces to this problem of estimating a mean of bounded random variables. And the tightness of those intervals or of those confidence sequences directly leads to faster audits. So less money and time spent on actually doing the audit. Okay, so that was the punchline and motivation. Now let's get into the details of betting and confidence sequences. So here is the formal setup. Imagine that we observe random variables x1, x2, x3, and I'm not actually going to say that it's x1 through xn. So this is some weakening that assumption, and we're just saying maybe we'll observe an infinite sequence of random variables. They lie in 0, 1, almost surely. So this is yeah. So we can say this without loss of generality, and we can also, so this is the assumption that we'll make, as Praneeth mentioned. Are these things independent? No, not necessarily. All they have to have is they can be dependent, but they just need to have conditional mean mu. And the thing that you're conditioning on here is the past observation. So at time t, xt just has to have conditional on the past mean mu. Okay. And so in particular, these are bounded and they have conditional mean mu, but this says nothing about whether they're continuous distributions. They don't need to be discrete. They can be discrete, continuous, like the first one can be discrete, the second continuous, the third a mixture of the two. And so there's no dominating measure for these random variables here. So it's a very composite problem. But as a familiar special case that I encourage you to keep in mind, if you're used to it, is just this problem of x1, x2, and so on, IID from some distribution P with some mean mu. So this is a familiar special case, but just keep in mind that assumptions 1, 2, and 3 are handling something slightly more general or much more general, and the algorithms that I'll present will solve that problem too. Okay. So here is this betting game. So this is basically just going to be some intuition for why one might want to construct that product thing that I had showed before. It's purely for intuition's sake. The correctness will come from mathematical details, martingales, and things like that. But this is a fun way to think about it. It really brings the math to life. So think about having a gambler, one gambler for each m in 0, 1. So let's fix m, being some number between 0, 1. So think about this as like a candidate mean. So if we think about having many potential means, you can think about this as one that we're like interested in looking at for the time being. So the gambler, here's basically the game. The gambler starts off with $1. For each time t, from 1, 2, 3, and so on, the gambler chooses a bet. And so the bet just takes the form of a number between -1/1 minus m and 1/m. So the range in which the gambler is allowed to choose this lambda depends on the m that we're considering up here. And I'll talk a bit more about the bet in a bit. Then we observe that random variable, xt. And this is the fundamental step in this game, is that the capital, kt, at time t, is updated as whatever they had before, plus whatever they had before, times the bet lambda t, times xt minus m. So notice that the random variables x1, x2, and x3, these are random variables, but the thing that we're going to be looking at is actually the wealth that is, or the capital KT that is accumulated in this specific game. So actually, let me pause. Are there any questions about maybe the details of this game? Something else I might mention. Sorry. Yeah.
So it's like always got some negative values and some positive values, regardless of that.
Yes.
Get bad, that is going to be less for
Yeah. So no matter what M is, you can have bets that are negative or positive, but the range will change. Yeah, it's a great point. Another thing I should say is that this bet lambda t, it can depend on all the information in the past. So at time t, we've observed x1, x2, x3, and so on, and we've also observed the capital that has accrued over that period of time. Lambda t can depend on all of that, but it cannot depend on the future, right? The gambler doesn't have any information about the future. They can just make their bets depending on the past. So these are basically the only two constraints, is that it depends on the past and it lies in this interval. So in this game, the gambler wants to make as much money as possible. So how should they choose lambda t? Let's think about 3 different scenarios. So first, what if the mean, I should have written conditional mean here, but I ran out a bit of space. But basically, what if that mean mu is much bigger than m? Well, then in that case, we can expect this term here to be positive in expectation. And in that case, lambda t the gambler would want lambda t to be positive, because in that case, you're basically saying, okay, my capital at time t is whatever I had before plus something positive. They don't want to choose a negative lambda, because then that would mean that their capital is going down. Similarly, if mu is much smaller than t, then we can expect this term to be negative in expectation. And so in that case, the gambler would want lambda t to be negative so that we could make this entire term positive, and then their capital would be, again, increasing in expectation. So that makes sense, but something interesting happens when mu is actually equal to m. So in that case, basically this term is in expectation 0, and then can they expect to make money or not? So I'll just expand on that a little bit. If we look at this mathematically now, under all the assumptions that we had made before, this capital process, when we plug in mu for m, so I'm using the color purple for mu instead of m. So when we actually evaluate it at mu, this forms a non-negative martingale starting at 1. It starts at, sorry?
non-negative plus the range.
Yeah, I was just going to say that, but very accurate. So it starts at 1 because we gave the gambler $1 to start with. It's non-negative because of this range. So lambda t having to fall in this range is exactly why this thing is non-negative. It's a martingale because, well, a martingale is just something that's conditionally constant in expectation. So conditional on the past, it has a constant expectation. So basically what this is saying is that if I look at the expected capital given everything in the past, I'm just basically rewriting what I had on the previous slide. This is the previous capital plus the previous capital times this term here. So if we look at this term a little bit more, this is just lambda t comes out of the expectation because I'm conditioning on x1 through xt minus 1, and lambda t only depends on the past. That's fine, comes out of the expectation. This thing is 0 in expectation. And therefore, if I rewrite this all out, it's just saying that conditional on the past, the capital is not expected to change. It's not expected to go up or down. And this is regardless of how the gambler chooses lambda t, right? It's like no matter how smart they are, no matter how much information they use about the past, or if they don't use any information at all, or if they're adversarial against themselves, they can't expect to make or lose money in this sort of game. So if I take just one particular example, and I was going to mention that there are many similar ideas in Schaefer and Wolf's books in 2001 and 2019 on game theoretic foundations for statistical inference and probability. But they were interested in a foundation of probability. Here we're still dealing with measure theoretic probability. We're just using some of these game theoretic ideas. So if I were to take a particular instantiation of that game that I looked at before, but looking at the actual martingale, so when we plug in mu for m, this is what some of these capital processes look like. So they jump up and down. Most of them start around like this value of 1 and they don't move too far. A lot of the time the gambler will just, like their money will just go really, really small, but sometimes they actually are able to make a lot of money. But very rarely, right? Like you can see only in a few cases did their money actually like shoot up and go above like $20. And this is actually something that can be made very formal. And this is by Jean-Ville. So Jean-Ville's 1939 PhD thesis said, it gave this result, that the probability that there exists a time t when a non-negative martingale exceeds 1 over alpha, this probability is at most alpha. So what is this saying? This is saying that no matter how long the gambler plays this game, they will never exceed 1 over alpha capital with probability at least 1 minus alpha. So let's just instantiate this at alpha equal to 1/10 or 0.1, then the gambler is unlikely to ever make more than $10. No matter how long they play, no matter how smart they are, they'll never make more than $10 with 90% probability. Okay, so if I take that previous plot that I had the previous slide, and I just draw a line at 10, so this is at $10, you can see that like most of these wealth processes stay below 10, and this region up here, this only gets achieved with some probability less than or equal to 1 over 10. So this is like the formalization of like what we observed on the previous slide. Let's say I looked at this statement, but I fixed it for a specific time, let's say 2000. And if I were to look at this region here, the statement like that the probability that some random variable exceeds 10 with probability no more than 1/10, this is exactly Markovs inequality, which you might be familiar with. It's like, one of the first things that one learns in a measure theoretic probability class, because it yields all these other inequalities like Chebyshev and Chernoff and things like that. But Markovs is a slightly more general statement in the sense that it works for non-negative random variables. But if you have a non-negative martingale, of course, all non-negative martingales are non-negative random variables, but if you have a non-negative martingale, then you get not just Markov, but you basically get the exact same Markov. So this is at the same level. You get the same Markov statement, but uniformly throughout time from 1 off to infinity. It's a pretty remarkable result. So as soon as you go from random variables to martingales, you have this like wonderful time uniform version of Markov. And this is Beal's inequality. Yeah.
Wait, why is this non-negative? Is the gambler also like, does lambda t also have to be less than or equal to kt, or is that like all of
it follows basically from this constraint, the fact that the gambler can only take bets between this range,
even though that doesn't have t in it?
Yeah, because sorry.
Oh, okay. I see. So each time, I see the amount they lose can't be
Okay. Right. And so, yeah, so intuitively, you can think about this as saying like, if you go to the casino with $1, you can't go home with negative $1. You can lose everything and you can make a lot, but you can't actually borrow money, at least in this idealized world here. Okay, so we're talking about this, and then remember I wrote this level set version of Hooftings inequality. It turns out that if you were to look at this from the game theoretic perspective, then if you were to look at what this process is, it turns out that this process is a non-negative super martingale starting at 1. So it doesn't look like we constructed this from a game necessarily, but there is like an underlying game that could be played where this is the wealth process when you plug in mu equal to m. So this is a non-negative super martingale starting at 1, which just says that instead of it being conditionally constant in expectation, it's non-increasing in expectation. So this just says that if you think about this from the game theoretic perspective, this is like a game that you do not want to play. It's like, no matter how smart you are, no matter how much thought you put into your bets, or if you're adversarial against yourself, you'll never make money, but there is potential downside. Like you could lose a bunch of money, but you can never make a lot of money. So yeah, this can be thought of as an unfair game in the same way that the previous one can be thought of as a fair game. And so so this is a similar plot where we have like those KT processes, and then here are the Hoofting processes in one very like extreme example. I'm giving this extreme example to show you like, sure, I have this same like Veal inequality thing where I can say that HT is never going to go above 10 with some probability bigger than 90%. But as you can see, it's actually much larger than 90%. It's like if I were to rerun HT many times, it's much more unlikely to go above 10 than the other one was. And this is because of it being a non-negative super martingale. And as before, this, if I looked at it at a fixed time, remember I said that that was basically Markovs inequality? Well, Hooftings inequality does rely on Markovs inequality. And so this is basically the region in which one would construct the usual Hoofting inequality, even though there is an underlying super martingale that could have been exploited. You could have applied Veal's inequality to it, but we only know this with hindsight. But the original Hoofting inequality is really using Markov. I'll touch on that a bit more later. But and so now to basically get the confidence set, we can then invert Veal's inequality. So this idea of inverting, the idea of like constructing a non-negative super martingale and then applying Veal's inequality to it and then inverting it has been either used implicitly or explicitly in a lot of different works, largely pioneered by Herbert Robbins, who I'll talk about in a bit, as well as Schaefer and Vogt, and also some work in like, I think this would be like management science, online learning, and then this is more recent, like confidence sequences paper, sort of like revisiting a lot of this Robbins stuff, and also some other work in safe testing. But so this idea appears in many different places. But here we're explicitly looking at this problem of bounded random variables and trying to make this thing as tight as possible. Basically trying to construct the best possible martingale that we can, apply Veal to it, and then see where we go. And so this set can be thought of as the set of all candidate means M for which the gambler did not make much money, right? So so the fact that this is correct is just, the fact that this is a confidence set, I'll tell you what kind of confidence set it is, but the fact that this is a confidence set just relies on the mathematical properties of martingales, Veal's inequality, et cetera. But it is also intuitive. If you think about, if the gambler is playing this game where they're unlikely to make too much money if mu is equal to M, and then I actually find out that the gambler made like $3,000, I'm going to be like, okay, that's probably not mu. But if, on the other hand, they're playing this game, they're trying to play really strategically, and still they cannot seem to make more than $10, then I can say, okay, that might be mu. So this is like an intuitive way to think about this type of confidence set. And so this is the guarantee that this confidence set has. It's that the probability that there is ever a time t such that mu is miscovered is at most alpha. So remember, this is a much stronger statement than what we initially set out to have. Initially, I said, let's construct a set such that the probability that mu is in Cn is probably that it's miscovered is at most alpha. Here, I'm saying not only is it miscovered with small probability at any fixed time, but uniformly throughout time. Or in other words, the probability that mu is in the intersection of all of these confidence sets is at least 1 minus alpha. So I'll talk a bit more about that. So this type of set that has this guarantee is called a 1 minus alpha confidence sequence. So I'll go on a quick detour on confidence sequences very quickly. But a lot of these, so the idea of confidence sequences, the definition and a lot of the exploration of their properties was largely can be attributed to Herbert Robbins in the 60s and 70s, along with many of his students and collaborators. So Siegmund Darling Lai and others. Wald wasn't, I don't think he was actually working with Robbins on this, but Wald did a lot of foundational work on sequential inference in the 40s. And a lot of those ideas are very much related because there's this duality between hypothesis testing and confidence sets. But yeah, so a lot of this was very early work by Wald, Robbins, and others. So the easiest way to think about what a confidence sequence is to think about what a confidence interval is, and then think about how a confidence sequence is different. So if I look at the guarantees of confidence sequences and confidence intervals, the confidence interval CI, I'll call them CIs and CSs for a second. CI says for every fixed sample size n, or for any fixed time, you can think about it as time, that for every fixed value of n, I have this small probability of miscoverage. The confidence sequence, on the other hand, has this guarantee uniformly throughout time. Or if we were to like look at the opposite, or the 1 minus situation, we can say that the confidence sequence uniformly captures mu throughout time, while the confidence interval just captures mu at some fixed time. So it's like basically if I took this for all expression and I put it inside the probability statement, then I've got this confidence sequence. So this is what these things look like. So this is not a figure from this paper, but it's from one of my other papers. But I think it's useful for just like looking at these two things. So in orange, the solid orange line on the outside, this is a confidence sequence, while the dotted green line is a confidence interval. And so what you'll notice is that the CI, it will mostly cover this true value of 0.4 in this example. It'll mostly cover 0.4, but at many times it'll miscover. It'll just jump up and down, it'll miscover, but like most of the time it's capturing it. So if you were to look at this sequentially, it's not valid, but at a fixed time, it's valid. The confidence sequence, on the other hand, is just a little bit wider, but what you get from it is that it uniformly captures that value. And of course, this is like a cherry-picked run of this sort of, to observe this exact phenomenon, but it is sort of a typical or illustrative run. But if we were to look at this a little bit more like holistically rather than on a single run, if we do like many simulations, what this plot on the right-hand side is showing is the cumulative miscoverage rate. So the probability of ever making a mistake. Sorry, it's there. Oh, okay. So the probability of ever making a mistake up to some time. So as you'll notice, like the CI starts at about 10%, and it steadily grows, it goes up, and then it will actually go to 1. So what that's saying is that if I'm looking at confidence intervals over time, at least in these confidence intervals or most confidence intervals, if you keep on looking at these confidence intervals, you are eventually guaranteed to make a mistake. You're eventually guaranteed to miscover at some point in the future. The CS, on the other hand, it starts very small, and then it steadily grows, but it will never go above 0.1, even in the limit. And so what this is saying is like, no matter how long I run these things, there's some good chance that I will not miscover. So this is just what I've said maybe too many times now, but CIs are valid at a single sample size. CSs are valid at all sample sizes. Okay, so that's the end of that detour. Let's talk about confidence sequences specifically for means of bounded random variables. So like I said, our confidence sequence takes this form. It's a set of all m such that this product function of m is lying below 1 over alpha. So it's the sub-level sets of this function, if I view it as a function of m. It's valid for lambda I, but what is a smart choice of lambda I? So remember I said like, no matter how, if mu is equal to m, you can think about this as being under the null hypothesis. If mu is equal to m, then no matter how I choose lambda I, the gambler cannot make any money. The gambler can't choose lambda I in some smart way to gain or lose money. But if you're under the alternative, meaning if mu is less than m, or if mu is bigger than m, then there must be some sort of smart choice of lambda. You would want to, basically, if there's an opportunity to make money, then the gambler's not just going to want to set lambda equal to 0 always, because of course, yes, they'll never make more than $10 guaranteed when the null is true, but also when the alternative is true. When mu is different than m, they're also never going to make money. So the idea is to somehow make money under the alternative. So what's a smart choice? So, okay, first I'll say there are lots of different smart choices. Like there are so many things that you can do here. You can spend a long time trying to think about what the best way to choose lambda I is. And we have a lot of those discussions in the paper. I'll show you one, which it's nice for 3 reasons. It's easy to think about. It's really simple, and it has some nice like properties of it being computationally efficient and things like that. So that's a great question. It does not have to be constant over time. It can depend on the past, right? So the gambler can choose lambda based on like previous values. So it can definitely change. It can be data adaptive, but yeah, but the reason I said that's such an important question is because on the next slide, I'll show some examples where it's just constant. So it's not necessarily, it doesn't seem like a good choice, but it is. So you don't want to choose it at one of the endpoints. So, okay, I wasn't actually planning on discussing this, but there's a very interesting paper by J.L. Kelly in 1956, where he's talking about basically this exact problem. He's totally not motivated by statistics. He's motivated by like information theory and coding theory over channel and things like that. But in there, he was like analyzing these sorts of like basically the wealth process of a gambler. It was a little bit different. It was like a coin flipping game, so it was slightly different. But basically, under that regime, there's like an optimal bet that you can make, that the gambler can make, and depending on what the mean of some coin is, the bias of some coin, and there's some like optimal bet where if you go just anything above that, you're guaranteed for your wealth to go to 0. Just think about them as someone who wants to make a bunch of money. So they want to like maximize the amount of their money over all time. Yeah. Right. Yes, you definitely can. So that's a great point. So the regime I was just talking about was one in which the gambler basically wants to have their wealth grow to infinity. So that's one example. Another example, which I'll talk about a little bit later, which is like, if I just want to make as much money by some specific time, I just want to make as much money by like round 100. Like maybe I have all of my life to play this game, but I really want to have money by the 10th day or something like that. You can think about that as an alternative. Yeah, something like that. So there are a lot of different motivations. These are great points. I didn't prepare like slides for that or anything, but yeah, if you want, we can definitely talk about that offline. Yeah. So yeah, it's a great point. So what we want to do here, so getting back to this, we want to choose lambda I in some way that is smart. And like was mentioned, this can depend on the past, but I'll show you one that actually just uses a constant value of lambda that is kind of effective. It's a little bit cheating because it's not exactly what I had written before. Think about, so I'll call this hedged Kelly betting. So the optimal thing that I was talking about before, where you want to grow your capital as much as possible, you want your capital to go off to infinity. That is called Kelly betting. And there's a whole line of literature on that in like different subjects. And so we were motivated by that. And we do have some algorithms that are akin to that, but this is not really Kelly betting, but we were motivated by Kelly. And so we named a lot of our algorithms after Kelly. So here's the example. You can choose lambda between -1 over 1 minus m and 1 over m, right? I can choose anything in here. So if I don't know which one to choose, I'll just choose all of them, or I'll choose a bunch of them. So for some large value of capital D, so I'll have like lambda 1, lambda 2, and up to lambda D. And then hedged Kelly betting or hedged grid Kelly betting is basically just saying, all right, I'll just use a fixed fixed constant strategy for each of these, and I'll take the average of all of their wealths. So before I did just talk about this particular wealth, this particular capital process, this product, but it turns out that you can just take the average of non-negative martingales. It's also a non-negative martingale, as long as the filtrations are the same, which they are here. Yeah, so it's maybe not very satisfying, but it does quite well. But this is basically here's a picture of it. The gambler takes their wealth, they split it up into chunks of whatever they had before, one divided by D, and then they make a bunch of constant bets here, and then they reap the rewards at the end. So this is basically like, if someone tells you, you have to pick a stock and make money from this stock, rather than choosing one stock, you just choose like 10, and then, but you have to divide your money up. So instead of having $100 in one stock, you put $10 in 10 stocks. So this is basically this idea. Yeah, so why use this strategy? It has good performance, and it forms an interval almost surely. So let me see how to do this. So here in this set that I had displayed before, notice that this is an implicit set. It's like the sub-level sets of this function. There's no guarantee that such a function would be convex or quasi-convex. So like maybe the sub-level sets are not actually an interval. Maybe they're not convex. Maybe they're like a union of two convex sets or something a little bit more crazy. But for various practical and computational reasons, we would want it to actually be an interval with probability 1. And this betting strategy of H.G. Kelly actually guarantees that. Yeah.
I happen to choose remember I so that the set that you had on the previous slide is not an interval.
Mm-hmm.
How do I interpret that result?
It's still a valid confidence set. Yeah, it is. It is weird. It is a bit weird. They're hard to come by, honestly. So there's two issues. It's like, can I prove that it's an interval, and is it an interval? So like often it really does seem like it is. But we were able to come up with some like crazy counterexamples at very, very small sample sizes with very, very extreme bets where like you don't get an interval. So it is a bit adversarial, but there are counterexamples to it. But in most practical situations, if you have like a sensible betting scheme, it will be an interval, I'm pretty sure. But if we want just some mathematical guarantees, this one guarantees it, probability 1. So yeah, and we also discuss Kelly betting, approximations to it, and other things in the paper. This is J.L. Kelly, Jr. Okay, so here on this slide, actually, let me just ask, I have 15 minutes, right? We go till 2? Okay. Oh, right, yeah, I was gonna say, have I been talking for an hour and 45? So, okay, so on this slide, I have just some different confidence sequences. Yeah.
I feel like we just moved the problem from choosing lambda to choosing D. How do we choose D?
Actually, choosing D does not matter too much. It's purely computational because you're basically doing it on like a finite grid. You could think about it in the limit, and it's like an integral. That is also a valid non-negative martingale, and we call that, I think, Kaplan's martingale, because there's someone named Kaplan who wrote this on a blog, which has now been taken down. But if you use the Wayback Machine, he discusses it. Yeah, so basically the idea is that integrals with respect to a probability measure of a martingale is also a martingale. So that's not too bad. But for computational reasons, you might not want to do that because you're taking an integral of like an n degree polynomial where n is growing. So but using this like capital D discrete makes it very computationally efficient, very easy. And just as a side note, all of those algorithms that I was showing before, it's like an implicit confidence set, but it's extremely easy to compute. Like if you can compute huge, like for huge sample sizes in like less than a second, it's very, very easy, but they are implicit. Yeah.
So it doesn't matter when they do D1.
Okay, it does matter. It does. You don't want capital D to be like 1 or 2, because then you're really not diversifying these potential bets. But when you get to like 10 and 20 and 30 and 100, it's like you really can't see a difference between them. So I think in the simulations that I have here, D is 10 or 20 or something like that. You can do 100 as well, but I couldn't visually tell a difference. That's an interesting problem too. Yeah, so here are a bunch of different confidence sequences, some that appear in the literature, some that are ours. And so similar story to before, where you have Hoofting doing well in this case where we have like a large, the maximal variance of 1/4. And then we have H.G. Kelly basically matching or improving on it. And then in this low variance regime, we have Hoofting staying basically the same. So this is not, this is actually not Hoofting's confidence interval. This is like this was not presented by Hoofting. This is like a martingale generalization of Hoofting's inequality. But yeah, still same sort of like idea. And then this H.G. Kelly thing does quite well. It proves on these other confidence sequences in the literature. And the only one you can see there that kind of matches or is close to H.G. Kelly is actually another one of ours, which just uses a totally different betting strategy, which you can interpret in a completely different way, but it also seems to be very sensible. But yeah, we can talk about that more later if people want. Okay, so the recap so far was that we formally set up this problem, the sequential problem. We described this sort of betting game and talked about this gambler who wanted to make lots of money and how they have all these games and how they're unlikely to make money in these games and things like that. And then we showed how constructing that game immediately implied the existence and construction of confidence sequences. So that's it for betting and confidence sequences. Now I'll just talk about fixed time confidence intervals using these ideas. If you just care about the fixed time setting, using some of these sequential ideas will really help here as well. So the first thing to note is that if the sequence of C's is a confidence sequence, then Cn at a fixed time is a confidence interval for any fixed value of n. So if I fix n a priori, then it's a confidence interval. And so you can see this by just, if I was just concerned about looking at these are confidence sequences, but if I looked at them at these two particular times, then what I have here on like the vertical axis, these are valid confidence intervals. So we'll basically use that, but you might be thinking, oh, well, if I have this uniform guarantee over all time, aren't I losing something by only wanting it at a fixed time? And then but I have this much stronger guarantee. It turns out we'll still have this like time uniform guarantee, but it'll be essentially useless everywhere except those areas that we really care about. And implicitly, I mean, it wasn't explicit, but implicitly, Hoofting and a whole bunch of other Chernoff methods like Bernstein inequalities and things like that, they're all doing this under the hood, but they're just using Markov instead of Veal. So we'll just use Veal. It'll gain us something, and you'll see what that is. So here's the confidence set. After some heuristic calculations, and remember, heuristic calculations are fine because lambda doesn't matter how I choose lambda, as long as it depends on the past and it satisfies that range, I can use whatever heuristic calculations I want to choose it. So after some heuristic calculations with an asterisk, because I have backup slides for it, but I won't show them right now, a good choice of lambda is to choose it in this way. So the important thing to note about this is that I've got two lambdas. One is for the positive side. I basically want to have power against against one end where like m is bigger than mu, and against one end where m is less than mu. And they're truncated appropriately. The important bit here is that they depend on the past, right? They're still predictable. Predictable meaning like at time t, it's ft minus 1 measurable. It's just predictable, but it also involves this value of n. So this is sort of like the regime where, like you were saying, you might want to have something that's tight at a fixed point in time. It's not like I just want to grow my capital off to infinity. It's like I want it to be tight at this time, in particular this time, and I don't care about anywhere else. So that's sort of the regime that we care about for fixed time confidence intervals. And then so I'll define this process. Don't worry too much about how it looks. It's a max instead of a sum for some technical reasons. Basically quasi-convexity versus convexity, but we can talk about that offline. The important bit here is that this tuning parameter, I'm essentially constructing a confidence set using statistics, and I have a tuning parameter, which is data dependent, and I did not need to do sample splitting. So typically, using data dependent tuning parameters is not okay in statistics. But in this case, we were able to use them without having to resort to sample splitting, where you essentially divide your sample by 2 and then you lose half your sample efficiency. Here, it was completely fine because we didn't choose them based on all of the data. We chose them sequentially over time based on the previous t-1 observations. Okay, so given these bounded random variables, I can construct this set, the sub-level sets of this previous kn thing that I had on the previous slide. This is a sharp confidence interval for mu. I'll show you how sharp it is in a little bit, but there's one more modification that we can use to get strictly tighter confidence intervals for free. So here's the intuition behind that. If C1, C2 up to Cn forms a 1 minus alpha confidence sequence, then so does its intersection, right? So if I have a bunch of sets which all uniformly contain mu, then their intersection must as well. And so I can essentially take the running intersection of a bunch of confidence sequences over time, and that's also a valid confidence sequence. And so this is what that looks like. Sometimes there's a lot of gains, sometimes there's not. But here, what you'll notice is like, so in green, I'm sorry if these are not colorblind friendly, I just thought about that. But so the green ones are basically the usual confidence sequences. The red are the intersections so far. So you can notice it's strictly tighter. You don't lose anything. And in particular, if you just cared about it at like, some fixed time of 100, then, so sorry, on the right-hand side, these are the confidence sequence widths. So so lower is better, basically. This is how wide the confidence interval is. And so if you were to take this running intersection, you'll notice that there's like this little gain that you make. But this can be important, especially when you're comparing against different confidence intervals and things like that. So taking this intersection is a strict improvement over the thing I had on the previous slide for free. And that's the intuition behind why it's correct. So, same sort of plot. Here's Hoofting, and here's this intersection thing. Now, this is mostly me just like giving my conjecture or like my own heuristic reasoning for it. The reason why we're not just matching Hoofting, but we're actually improving on Hoofting a little bit, even in the case where Hoofting is tight, is because we are taking this running intersection where Hoofting could have done that, but because we have the benefit of hindsight, and we know that Veal's inequality can be applied to a super martingale rather than just Markov to a random variable. We have this benefit of hindsight, so we knew we could take a running intersection, and that's why we're able to just beat Hoofting a little bit in these sort of regimes. And then, of course, in this low variance scenario, Hoofting is about the same, and ours nicely adapts to the underlying variance. And this is the same plot that I showed on like the first few slides. This is just the confidence intervals revisited. Okay, so the recap of those fixed time confidence intervals is that we use these sequential ideas for fixed time inference. Most notably, we had these data dependent tuning parameters, right? We were able to not use sample splitting and actually create these data dependent tuning parameters in a totally fine way. And we also use this strictly stronger than Markov inequality, which is basically Veal's inequality, but if I just apply it at a fixed time by taking a bunch of intersections, it's always tighter than Markov. And so we benefited from these two things here. So here are the main contributions of this work. As I wrap up, we developed these non-parametric confidence sets for means of bounded random variables. And to do this, we use this betting intuition. But the correctness, of course, was through using martingales and Veal's inequality and things like that. They're valid in both sequential and batch settings, but we can use the sequential ideas in the batch settings to get tighter confidence intervals. They outperform the prior work that we compared to on this problem in sometimes very significant ways. And the two things that I didn't talk about were these closed form empirical Bernstein confidence sets and the extensions to a different type of sampling, which is sampling without replacement, where you're just taking like numbers from a bag instead of like drawing things from a distribution. So we have extensions to these two things. They're in the paper. I also have backup slides if you want to talk about them, but these were the main contributions. So yeah, that's everything I had to talk about. I really appreciate being given the opportunity to come here and discuss some of my work with you. This is a lot of fun. And here my website and Adi's website if you want to check out some of our other work and what we're up to. Thanks. Yeah.
Maybe your backup slides will answer this question, but like for example, Hooftings and even empirical Bernstein, the normal old empirical Bernstein, have the property that if you want to compute them in sort of an online fashion, like I'm getting samples and I want to compute them like at each time step, I can do the updates in order one time and order one space. Right? I can just like update a running mean, update a running variance, and do the computation.
Mm-hmm.
Can you do that here?
So it depends. Are you talking about confidence intervals or confidence sequences? Yep, you could. It's order one. Yeah. So you're basically, yeah. Let me see if I have blah 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 blah. Let me see. So this is the form of the predictable mixture empirical Bernstein thing that we developed. So it looks a bit funky, but it is closed form. Everything is just easy to compute. And so basically this basically gives you an order one time and space update for the mean. Then you plug that into here. It's also an order one time and space update for the variance. You could do something more complicated where you have, instead of mu I, you could have mu t minus 1, but that's more computationally expensive. So I did this actually instead, even though you could have done the other thing. And then lambda t just uses these two, and then you basically plug it into psi e, and then you plug it in up there. So it's like a backwards plugging in, but yeah. So, but of course there are other betting strategies that might not be closed form, and in practice, like some of closed form, but also have constant updates. And sometimes it's not too bad. Sometimes it is. In all the ones that I consider, I think they're all order one time and space complexity. Didn't think about it too much because they just ran pretty fast on my laptop, but yeah. Unbounded random variables. Let me say about unbounded random variables. Yeah, there's a lot you can say. Depends on what kind of unbounded random variables you have. So, for example, not in this work. Okay, maybe I should first say what we do in this work. So, for one thing, you can have one-sided confidence intervals or confidence sequences from, one-sided confidence intervals or confidence sequences from lower bounded or upper bounded random variables. So that's one thing, but maybe that's not as satisfying answer. Another thing you can do is you can construct confidence sequences or confidence intervals from quantiles, for quantiles rather than means. So if you're just interested in quantiles, then you can have confidence sequences and confidence intervals for any distribution, which is not too surprising, I guess, because those already exist sort of with DKW style inequalities. But yeah, if you're just interested in that, then this sort of framework can actually give you quantiles. We didn't talk about it too much, but there's a note about it I think in the summary of the paper. And then if you have like more structure to your random variables, like if things are symmetric, for example, then you can construct confidence sequences for the mean. That was not discussed in this paper. I can't remember where that was from. It's one of Aditya's papers. I think it's a little bit more than that, but probably uses that information, but it deals with these sort of self-normalized exponential super martingales. I think they might actually be martingales. I can't remember. Sorry. Yeah. And then if it's like nothing about the random variables except maybe they have like some moments, for example, then you have to resort to sort of central limit theorem type arguments. And there actually is a sequential central limit theorem, and that was one of my other papers that I did not present today, but that figure that I had of the confidence sequence versus the confidence interval, it's from that paper. Yeah. 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 So that was considered actually by Robbins. So Robbins had like basically, so if the tails are thin, that's essentially just a time uniform sub-Gaussian confidence sequence. Yeah, Robbins considered that scenario explicitly, and then this was greatly expanded upon in a paper by Steve Howard, Adi, and Steve's PhD advisors at Berkeley, John McAuliffe and Chaz Seacon. They considered sort of like not just the generalization of sub-Gaussian situations, but basically any Chernoff situation. So if you have like sub-gamma, sub-exponential, sub-Bernoulli, and many other, not just the Chernoff stuff, but some other ones. But that was sort of the main, I think that was the motivating aspect of it.
One more question.
Yeah.
So you showed this from the beginning where it's like, oh, take the everything mean and add like log 1 over alpha over.
Yeah.
So that kind of bound is the bound that you maybe more than half that.
Right. Yeah.
So one way your approach is used to give a like compact thing like that, a better compact thing like that, or should do it really go back to this?
Good question. I guess it depends on your motivation. So if you just want to use, if you just need a bound for the mean of something, and those somethings are bounded, you can of course use Hoofting, and it has that nice closed form expression. You can use this closed form expression. Maybe you'd argue it's not as nice, but it is a closed form expression. And then yeah, if you wanted to use the betting style confidence sequences or confidence intervals, those will work as well. But I guess it depends on whether you're interested in just getting like a bound where you say, oh, this thing is big O of 1 over square root n. These methods, if I'm to make just a very general statement, typically these are not improving on the rate. Like Hoofting is rate optimal. So that's not the problem that is being solved here. It's more in the constants and adapting to those specific aspects of the distribution. So like it's maybe Hoofting is rate optimal for any bounded distribution, but then if you have like some smaller variance, you might want to adapt to that particular problem. And in that case, yeah, you would maybe want to use something like this. It also depends on, if you're writing something theoretical, or if you have to like code this up, and then if your problem, kind of like those things that I discussed at the beginning, like the prediction sets for like those tumors, or in the election auditing example, there we could have just said, oh, this is correct. I could have just used Hoofting and it's correct there. But the problem was there, like for the practical instantiation of the problem, the tighter confidence set gave me desirable properties of that like particular solution. So there you'd want to use something like that. Yeah. Any other questions?
Do you know hedge-cutting confidence sequence is always like that Hoofting?
Yeah, there's a result in the paper of that form. It's not as satisfying in the sense that you wouldn't want to use that one. So if you really just want to beat Hoofting, then you can do that in a very formal way, guaranteed. It's just using a deterministic inequality. But typically you wouldn't actually want to do that. And in practice, it seems like it improves on it. But if you are really just concerned with like, is this thing beating Hoofting, you can instantiate one particular lambda.
Just run both of them and take the minimum of those.
Well, then you'd have to take a union bound.
It's only like you are doing only alpha, right?
Yeah, you would lose
alpha, you would be correct.
Yep. But that will often matter quite a bit. Yeah. Yeah, the constants. Yeah. Exactly. Okay. All right. Well, thanks so much.